Sorry for this. So now, today we have Michele Burrello, who will speak about discrete abelian lattice gauge theory in a ladder geometry. Please.
Thank you very much, Andrea, for the very kind invitation, and thank to all the organizers for indeed organizing this workshop in such a difficult time. And indeed, today I would like to speak about gauge theories, since this is a workshop about gauge theories, and I cannot just a second. Okay, and this is work done in collaboration with my former master student, Jens Nguyen, who is currently in Aarhus University, and my postdoc, Chi-Min Chun, who just moved in Taiwan as assistant professor. So this is an outline of the talk. And first of all, I would like to introduce a few very basic things about discrete abelian lattice gauge theories. And then I would focus on a specific model that is the Zn lattice gauge theory with X matter in ladder geometry. And my choice of the ladder geometry is due to the fact that it allows us to interpolate somehow between 1 dimension and 2 dimension and to apply a lot of one-dimensional technique for this study. So we see that in this model there are interesting limits, the limit of the pure lattice gauge theory and a quantum clock model limit. And in particular, one of our main results is that if we increase n up to 5, we have the emergence of a gapless Coulomb phase and Brzezinski constellates and Thouless phase transitions that separate this gapless phase with the surrounding gapped phase. Therefore, we will explore the general features of the phase diagram of this model, and I will mention some of the properties of the phases that emerge. In particular, we can consider screening properties. So the framework over which this work has been developed is the effort of applying quantum technologies and techniques that have been used to tackle condensed matter physics problems, also in other environments such as lattice gauge theories. And in particular, just to give you a broad overview, in the last 10, 15 years, there have been many groups worldwide who are really pushing towards having a strong development of quantum technologies. And in particular, one of the most interesting developments is the possibility of experimentally applying quantum simulations for the study of complicated many-body physics problems. And these quantum simulations, they come different kinds. And here I would like to briefly sketch the fact that typically we have digital quantum simulations that, for example, are the ones usually carried out with ion traps and with superconducting circuits, in which we try to simulate the dynamics of some many-body problem by decomposing it into simple gates as in a quantum computer. And then there are also analog quantum simulations, such as the ones typically carried on in ultra-cold atom environments, in which we aim at mimicking the Hamiltonian that we want to simulate through a physical system that displays a similar Hamiltonian, at least under some controlled conditions, for example, in the low energy theory. And in both cases, it's customary that we can simulate systems with a limited degrees of freedom. So it's very hard to go towards the simulation of degrees of freedoms that are continuum degrees of freedom, such as the ones that you usually find in field theory. But at the same time, if we discretize the degrees of freedom of this many-body physics, we can nevertheless say something about models of interest. And a similar philosophy is applied in the realm of tensor networks, of numerical simulations. And indeed, there have been many efforts to develop more and more precise information tools, quantum information tools for discussing what are the properties of quantum many-body physics. And at the level of method, I would say that tensor networks provide a very powerful tool to simulate interacting phases of matter and also to classify them, as we saw in the recent days. And more in general, there are many condensed matter theory tools. In my case, I use a lot of bosonization and quantum field theories to understand what are the main properties of the phase diagrams of several many-body physics problems. So I want to stress again that in many cases, it is convenient to discretize the degrees of freedom of the underlying model. And in particular, we can wonder what happens if we apply these technologies to the study of gauge theories. Of course, gauge theories are at the backbone of our understanding of the world, especially if we think about the standard model and the QCD. That is, so gauge theories in general are what is describing these particle physics. And then we have emergent gauge theories that are used to model very important features and universality classes in a lot of different contexts. In particular, here I am considering the fact that very often quantum speed liquids or exotic superconductors or more in general quantum antiferromagnets display properties that are due to the fact that there is an underlying gauge theory that is describing the low energy properties of these models, and also concerning topological self-correcting quantum memories like the toric code. This is indeed a case of gauge theory. So as I was saying, there has been a huge effort in trying to understand more and more the physics of gauge theories by exploiting new kinds of tools. So traditionally, we have Monte Carlo simulations that have been very successful in understanding, for example, the spectra of hadrons. But there are also limitations of Monte Carlo simulations due to the fact that we have the fermionic problem, the sign problem for a dimension, or it's maybe complicated to include a large particle density. So we are in process of trying to develop new tools for the description of these complicated models, also to obtain a complementary description of lattice gauge theories in this case. And in this respect, we may think that so the path towards the simulation truly of QCD is very long, but we can do it stepwise, a step after the other, and we can begin about considering what happens in 1+1 dimensions. And there have been many works who understood, for example, what is the effect of truncated the Hilbert space on the Schwinger model. And so essentially, nowadays, we have very good dmrg studies of all one-dimensional models, both abelian and non-abelian. And then we may target two-dimensional systems with more and more complex kind of gauge groups, moving from abelian to non-abelian. In this respect, the work that I'm doing concerns abelian groups, Zn groups, and in particular, what happens in a sort of intermediate situation between 1D and 2D. So in a ladder model, the ladder model is the simplest model in which I have the plaquette terms in my Kogut and Susskind Hamiltonian, and therefore it's the easiest example of a model that displays both electric and magnetic charges. So of course, if I consider lattice gauge theories with Zn symmetry, a huge amount of work has already been done, starting from the seminal work by Fradkin and Shankar. And we know essentially what are the main features of all the phase diagrams of these theories. So here, just to remind you a little bit, I am considering the phase diagrams of a Z2 lattice gauge theory in 2+1 dimension and a U1 gauge model again in 2+1 dimension. And one of the most important differences is that in the Z2 case, everything is gapped. Namely, I have two different gapped pieces of matter. One is deconfined and topological. The other is confined and displays a well-known crossover between the confined and X regime. And instead, when I consider a U1 gauge theory, typically things become gapless. So I have phases that display gapless photons and are Coulomb phases, and phases that display Goldstone modes, and so essentially they have a gapless matter. And therefore, in this attempt of discretizing the degrees of freedom and going from a Zn to U1 theory, it may be interesting to understand how the gapless phases emerge. This typically depends on the dimensionality that we are considering. And what I'm telling you is the result that we get essentially in one dimension, where we have that by increasing n at n equal to 5, there is a gapless phase that emerges. This is not really stable when we consider 2+1 dimensional systems, but still, I believe it's important to get an idea of what is the path that goes from a Z2 model to a full U1 model in which I indeed increase my discrete number of degrees of freedom towards U1.
I'm sorry.
Yes.
So this is in 2 dimension, this phase
This is
diagram?
2+1
2+1
dimension.
Yes, and what is lambda?
So now I'm going to explain it, but there are two parameters that I will use. G is telling you essentially it's the electric charge, so it's telling you what's the ratio between the electric field term and the magnetic field term. And the lambda instead is the inverse of the mass, which is also related to the tunneling term. But you will see it immediately. Okay. Other questions? No. Okay. So let me begin introducing the model that I'm going to address. So the model, it's here, and it's depicted in this picture on the ladder. And in particular, we must consider two different sides. So there are the matter sides that are represented by the squares, where matter degrees of freedom live, and the circles instead represent the links over which the gauge bosons live. And in my case, I am considering a lattice gauge theory model in which both the gauge bosons and the matter are represented by Zn variables. So in particular, I will use two sets of clock operators to describe what's going on at the level of the matter and at the level of the gauge field. So both the squares and the circles for me are sites that display n orthogonal states, so a local Hilbert space with n orthogonal states. Therefore, you can look at the fact that in this ladder, the unit cell includes these five sites that I drew inside this rectangle here, and we will introduce several interactions to implement a congruence task in the lattice gauge theory. So in particular here, I would like to introduce the operators that I will use to build all these interactions. And these operators are the sigma and tau operators that are n times n matrices, and they live on the boson, gauge boson sites, so on the circles. And essentially, the idea is that sigma represents the connection, so it's related to the gauge field A, and tau represents the electric field. And these two operators on the same site commute by following this relation. So they have this commutation relation. Then, analogously, I will introduce two set of clock operators for describing the Higgs matter. So in particular, I'm considering frozen Higgs matter such that the modulo of the Higgs operator is constant, and I just consider its phase, and it's phased is quantized by taking n possible values. So in this case, I will have these zeta operators that are the annihilation and creation operators for this X matter, and eta instead is an operator that is the exponential of the electric charge of the matter. And the commutation relation that I'm considering is indeed this one. So when I commute zeta and eta, I will pick up a phase that is e to the I 2 pi over n. So in particular, I can choose any representation I wish of these clock operators, but in any case, they are n times n matrices, and one possibility is to take a basis for the description of the Hilbert space of both the bosonic degrees of freedom and the matter degrees of freedom, such that tau and eta are diagonal, so the electric charge and the electric fields are diagonal, and indeed they assume eigenvalues that are the nth roots of the unity. So that you may think about tau and eta being operators that are indicating a certain value of the electric field of the charge, like the ends of the clock that I am representing here on the right. And instead, the zeta operator that are adding or subtracting a charge are moving, allowing transitions from different values of the charge. And the same is true for the connection that allows transitions between different values of the electric field. So yes. Sorry? The time is continuously taken. I must say that here I'm not looking at the dynamics in this work. So we will mostly look at properties of the ground state and considering what happens at zero temperature, and therefore we will deal with 2-point correlation functions or string correlation functions calculated over the ground states. Other questions? No, okay. But yes, it's a quantum model in one quantum dimension, and I'm not quantizing time. So let's go on describing a bit what are the elements that I want to include in the Hamiltonian, and it's the standard Kohut-Saskin in the Hamiltonian. So we have two elements that involve only the gauge boson degrees of freedoms, and they are represented by the blue square and by the yellow dot. So it's the first two elements here in this first row. Sorry for people on Zoom. And here we have the blue term is the Plaquette term, so 1 over g is the amplitude of the Plaquette term, and it accounts essentially for the magnetic flux piercing a plaquette, so that if I imagine the particle moving around counterclockwise one of these plaquettes, it will get a phase, and this phase is described by the product of these 4 sigma operators taken on the links that define the plaquette. And instead, the yellow dot is this operator tau plus tau dagger, and we will have it again on all the links of the ladder, and it is an energy cost for the electric field. The other two operators that are characterized with this coupling constant 1 over lambda and lambda are instead related to the matter degrees of freedom. So the first one is essentially an energy cost for the charges, or you can see it as a kind of mass term that is an on-site term that lives in the squares of the ladder. And the second term is the hopping of a matter particle of a charge, and this hopping is mediated by the connection, so by the sigma operator. So you see that here what I'm doing is that I am annihilating a charge 2 pi over n here, and I'm moving it in a neighboring square with an additional phase that is determined by this phase, by this operator sigma. So these are the first term that enter in the Hamiltonian in this gauge invariant description. Why do I say that it's a gauge invariant description? Because I have local gauge symmetries. And in particular, local gauge symmetries are represented by this red combination of operators. which seem complicated, but let us look at it step by step. So in particular, what I want to emphasize is that we can try to rederive on a sort of continuous level what are the corresponding operators to my elements in the Hamiltonian. And as I was telling you, we have that the plaquette term is related to the magnetic flux. The Hoping term is indeed the Hoping term that you will find in QED. And then we have that tau plus tau dagger is morally related to the energy cost of the electric field. So it's essentially going towards E square, and theta plus theta dagger is a master. Then at this point, we may wonder, yes, please. Yes. The second intermediate, okay, yes, I didn't mention about this notation that I'm using. So I am calling with up the degrees of freedom that live in the upper leg. Down are the degrees of freedom in the lower leg, and 0 are the degrees of freedom in the ranks. Yeah, yes, they are operators, exactly. So this one is along the legs, and this one is along the ranks. Okay? Other questions? Yes, please. No, I must admit that here I am addressing the Zn lattice gauge theory for the sake of the Zn lattice gauge theory. However, I believe that we can make more rigorous this limit by considering indeed what is my parameter G in a proper continuous limit. So yes, it combines both the lattice spacing and the electric charge. So G is proportional to electric charge squared, and there will be some dependence on the lattice spacing that we should take care about. No, I'm not adding. So you mean a static potential? No, I have frozen it. So let us imagine that, so here you see I'm taking just the phases. So if you think about the field force or the Mexicanet, what I'm telling you is that the X mode has been frozen in its ground state, and then just taking care about so that this is a limit that captures some of the physics in the continuum model, not all of it. Other questions? Okay, so the other thing that I was mentioning is about the gauge symmetries, the local gauge symmetries. And one can see that these kind of operators commute with the Hamiltonian. And in particular, you may interpret this weird combination of operators. So we have 3 taus and an eta. And the 3 taus are the exponential of the electric field, so that essentially they become the exponential of the divergence of the electric field entering in or going out from a matter site. So takes these 3 link degrees of freedom into account, and the eta instead is just telling me what is the charge. So to impose that this operator is equal to 1 on the physical states is like to impose that the Gauss law is fulfilled. So for the moment, what I'm going to do is to consider a setup in which I take the Hilbert space and I take just the subspace of this Hilbert space in which all these gauge constraints are equal to 1, which means that I do not have any static charge in my model. Then I may introduce static charges to see confinement properties. Okay? So, yes, sure. Yes. So this doesn't commute with the tunneling term because so the way I see it is that here, this is a term that depends on the charge, so on the phase of this Higgs field. And when I apply this zeta dagger term, I'm increasing by 1 the phase of eta on this side, and I'm decreasing by 1. So the way I see it is that this for me is the cosine of 2 pi over n times the charge. And so being diagonal in the basis of the charge, I would consider it as a mass term. And instead, this is something that goes like psi dagger, and I would consider it as a kinetic term. Okay, of course, I can also use different bases. And so on a gauge perspective, this is the term that is diagonal in the irreducible representation of the gauge group. And instead, this is telling me what are essentially the tunneling operators. Okay. Yes. This is a very good question. I'm considering mostly open boundary conditions, and there are different kinds of boundary conditions that I could take. And I didn't want to go too much into detail, but let's flash about it briefly. So here you see that if I want to have an integer number of unit cells, I need to have rough boundary conditions on the left. So here I'm considering boundary conditions in which I begin with the gauge bosons, and instead I'm considering smooth boundary conditions on the right, so that here there is no matter can go out. So in this case, I am not considering, for example, a conservation of the total charge number, because I may add tunneling operators that are kind of incomplete here, in which I have just a sigma zeta term. And this breaks a global Zn symmetry that I have. And it will be useful in a while when I tell you about the clock limit. On this side, instead, I should include the fact that there are 2 additional gauge constraints, that instead of having three links involved, they have only 2 links involved. However, about our numerics, we often did numerics on both smooth boundaries, or on rough boundaries, or smooth rough. So we checked different kinds of boundary conditions. We also did some calculation on periodic boundaries, but periodic boundaries also for dmrg, it's usually a bit more demanding. But if you're interested, maybe later in fact we can discuss about the effects of boundary conditions, because this influences indeed the kind of degeneracy of ground states that I expect. Mm-hmm. Yes, so if I have periodic boundary conditions, as you say, there will be a sort of Wilson loop going all around. And in the limit in which I do not have electric field terms, for example, this is the symmetry of my system. So yes, I need to be a bit careful about that. Or for example, here, if I have open and open boundary conditions, so smooth and smooth, I may add electric flux line that correspond to changing the theta vacua of the theory, for example. So it's an electric field background that I may include, not with these boundary conditions, but when I have them smooth and smooth. So yes, there are a lot of things one has to take care about boundary conditions, and for the sake of simplicity in this talk, I didn't want to address all of them. Okay, so I move on. So this is a brief overview of the things that I'm going to describe and of the phase diagram. In particular, this is the phase diagram for Z5 theory. And what is important is that I will deal with the phase diagram as a function of these 2 parameters, G and lambda. So I remind you that G is entering here as the coefficient of the electric field term and the inverse of the Plaquet term, and lambda instead is the inverse of the mass term and the coefficient of the tunneling term. This is a customary parameterization, for example, if you take the book by Eduardo Radkin. And And in particular, there are two limits that are more easily understood. One is the pure lattice gauge theory limit. So when I send lambda to 0, the matter decouples. And we see that this is kind of trivial. And then there is another limit that is the quantum clock model that I will describe soon. So before discussing the phase diagram, let me go to analyze this limit. So this is the pure lattice gauge theory limit. So I forget about the matter. I consider just the gauge elements. And in particular, I can choose a specific gauge to study the model. I choose the axial gauge. And for the axial gauge, what happens is that I have essentially only the degrees of freedom on the ranks that allow me to describe what's happening on this limit. So after doing this mapping and this degree choice, you see that what happens is that I have the first two terms that are the plaquette term and the electric field term on the ranks, they give rise to a quantum clock model. And instead, the third term that appears here is a non-local term, and it corresponds to the electric fields along the legs. So here I have essentially a quantum clock model plus an additional term that is essentially corresponding to disorder operators. It's easy to see that this behaves like a model with a single gap phase until G is not equal to 0. So for any G different from 0, I have the same thermodynamic phase. And this can be understood as a confined phase. So one way of seeing this, for example, is to take a duality. And again, for the sake of simplicity, I'm not doing it. But if I take a duality, this model becomes dual to a model just with local interactions. That is a kind of a clock model in transverse plus longitudinal magnetic field. So if you consider what happens to the Ising model when I add the longitudinal magnetic field, I have that there is only one big gapped phase. Yes. So for me, at the level of this gauge, if I write it in this gauge, it's non-local because you see I have these string operators. If I consider the previous description, so before imposing a specific gauge, I would call it local, despite the fact that I have the gauge constraints to be observed. So essentially, by choosing a specific gauge description here, I am essentially integrating out some of the degrees of freedom. And what happens is that to describe terms that originally are local, just electric field along single links on the legs, what I get is that I need to express them as the product of several gauge constraints. And that's what gives me this weird string. So at the level of a model, in the dual picture, you could consider it as a local model for the magnetic fluxes. Namely, the first term would be the mass term for magnetic fluxes, is the term indeed. It's the energy cost for adding a magnetic flux. The second term is the kinetic energy for the magnetic fluxes because it nucleates opposite pairs of magnetic fluxes in neighboring plaquettes. And the third one is a term that introduces a magnetic flux on any plaquette from the outside, from the leg side. So I would call it local, but we can discuss about that. So I was telling you that the physics of this is the physics of a confined phase. And this is easily understood when I consider the introduction of static charges. So static charges are violations of the gauge constraint. The gauge constraint was telling me that that product tau 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 times theta was equal to 1. Here I'm putting it to be equal to e to the 2 pi over n in one side and e to the minus I 2 pi over n on the other. So essentially I'm pinning down a charge that is positive on this side and it's negative on this side. And I can look at the distribution of the electric fields that come out of that. And this distribution depends a little bit on the chosen parameter for G. So if G is very large, I'm essentially moving towards a system that is a product state of eigenstate of the tau, so product state of the electric field pointing in some direction. And what happens is that in the presence of these two static charges, the situation that the state that minimizes the energy is a state with an electric flux line that connects the two charges. If I decrease a little bit G continuously, I will see that the electric field percolates also on the other leg. However, these two kind of states are adiabatically connected, so I do not close any gap there. And it's different from two-dimensional. Two-dimensional would have a phase transition between confined and deconfined phase. Here instead, I see only the confined phase for any G positive. Instead, for G equal to 0, it's a bit pathological and I get a deconfined phase. So in particular, I can study also the level of perturbation theory, what's going on, and I can calculate the string tension associated to the introduction of two charges. So I look at the energy of the ground state with and without these two static charges as a function of the distance of the charge. And I see that both for G very small and for G very large, I have a linear behavior of the energy with the distance of the charges. So the farther away are the charges, the longer is the electric field line and the more energy I have to pay. So this is the trivial confined phase in the pure lattice gauge theory limit. And in particular, by doing some perturbation theory, I can also find out what are the limits of the behavior of this string tension. For G small, it will go up as a G cube, and for G large, it's linear in G. Yes? No, this is general for any Zn. So this plot is probably for Z3. I should check that. But this fact that I get a confined phase over the whole pure lattice gauge theory in my ladder geometry is true for any N. So if N goes to this is an interesting point. So the fact is that the gap of this phase will go down like 1 minus the cosine of 2 pi over n. And I must say that I cannot find any finite critical n over which this happens. So I cannot pinpoint the reason n such that yet. So here, strictly speaking, the gap decreases like 1 over n squared, but so, well, 1 minus cosine of 2 pi over n, but everything will have a finite, although small gap, every finite n. Okay? I'm going to the clock model limit in which this is different instead. Other questions? Okay, so for the moment, I would like to go now to speak about the other limit, the quantum clock model limit. And again, this is a limit in which I have that the Plaquet terms become very, very strong and the electric field is switched off. So I'm imposing that in the system there are no magnetic fluxes. And at this point, I can use again the axial gauge choice. And what I get is that in this limit of G going to 0, the cognatus asking Hamiltonian becomes the Hamiltonian of a quantum clock model on this ladder geometry, which is a bit peculiar. Now, let me remind you that about quantum clock models on a single one-dimensional chain, we know a lot about it. And in particular, we have that for Z2, the model becomes the Ising model, and therefore we have two gapped phase, order disorder with an Ising phase transition. For n equal to 3, we are in the universality class of the Potts model. Again, we have order disorder phase and the Potts phase transition. For n equal to 4, we have a model that is essentially equivalent to the Ashkin-Teller model. And again, we have order disorder phase and the phase transition with central charge equal to 1 at the center. And for n greater or larger than 5, we have that a critical and extended phase appears that is characterized by a C equal to 1 phase, so it's a Lattinger liquid phase if you wish, and it's separated through BKT phase transitions from the ordered and disordered phase. Something similar is going on to happen also in our ladder geometry. Please.
So this is the same diagram or the same phase structure you get in the purely 1+1 dimensional quantum clock model, right?
So the one on the left is, yes, I was recalling what happens in the 1+1 dimensional
I see.
And we will see that for the ladder, there is some subtlety coming out because we have twice the degrees of freedom. And well, I will show you soon.
Yeah, okay. So I was going to ask precisely that, where you get 2 copies of it. Yes, okay.
Yeah, there is some interplay. So I need to distinguish a spin and charge sector.
Okay. You're going to talk about it.
Let's look at the results of the dmrg. And in particular, if I want to investigate in this axial gauge whether my phases are ordered and disordered, I can define an order parameter. This order parameter morally in this gauge is zeta. If I am careful and I think back about what is the meaning of zeta in this lattice gauge theory, I need to find a gauge invariant operator. And it's an operator that takes a charge from the boundary and brings it in the site R through this kind of operator. So I will have a string that is the magnetic string, the connection string, times zeta. And for these, for example, it's important that I have open and smooth boundary conditions, because otherwise I should only take 2 point correlation functions of the zeta. So I look at boundary conditions that are smooth and rough on the left and the right. I calculate the expectation value of this parameter, where r is the distance from the smooth parameter. And well, in particular, I take r in the middle of the chain. I look at this order parameter, and I see that for, well, easing is not reported, but for n equal to 3 and 4, I have the signature of a single phase transition. And we get disordered phase for small lambda. Indeed, lambda is the ferromagnetic coupling. So for small lambda, we are in the paramagnetic phase. And on the right, instead, we have the ordered phase in which this order parameter becomes different from 0. And in principle, one can do a precise finite size scaling and check that we get the expected critical exponents. Exactly. So the point is that if I choose this specific gauge, the order parameter is local. But this is an artifact of the gauge choice that I made. If I look at the original model and I simulate it all, what I get is that this order parameter is non-local, as you were saying. So it's a string attached to the zeta. If I choose a different gauge, for example, the unitary gauge, that here I'm not writing, but it's the gauge in which I consider just the gauge degrees of freedom, it's non-local as well. And indeed, our dmrg calculation, for example, were done in this unitary gauge in which this is a non-local order parameter. Okay. Indeed, if I care carefully about the boundary conditions, the results are the same. So if in doing my gauge transformations, I care also about the boundary conditions, everything works fine. And what I wanted to emphasize is instead that in n equal to 5, I have a gapless region that appears in the middle. And this can be distinguished as a region in which in the thermodynamic limit, the order parameter would vanish. But the way in which it vanishes is not exponential, it's algebraic in the system size. But we will have better indications of the appearance of this algebraic critical phase. So for n greater or equal than 5, as in the case of the single chain of the clock model, we have this gapless phase in the middle. So when we have a gapless phase in the middle, for me, it's interesting to see what is the phase transition between ordered disordered phases, so the 2 gapped phase and the gapped phase in the middle. And here I want to argue that the phase that we find is separated by Berzikny-Kolstadlitz and Tauser's phase transitions from the outside. There are several tools that we can apply in this analysis. And first of all, we have to show that we truly have a gapless phase, which is C equal to 1, so Lattinger. And the best way to do it is to consider the entanglement entropy and make a fit with the Calabrese-Cardi formula. And we see that it's clearly C equal to 1. So in our numerics, was C equal to 1.01, or depending on the point. So that the fit works very well. We know that there is this kind of Lattinger liquid phase in the middle. And let us look instead at what happens at the phase transition. So one observable that is very useful is the fidelity susceptibility, which is essentially depending on the overlap of the ground state as a function of the parameter, in our case it will be lambda, with the ground state with lambda plus delta lambda. And this fidelity susceptibility divided by the volume is shown to have a maximum at the BKT phase transition. This maximum is a peak that doesn't diverge with the system size. It's going to a finite value, and it's going to a finite value with a peculiar scaling. So the correction goes as 1 over log L. This has been shown by Becqua and co-workers in several different works, and can be argued based on Weston-Minovitten models. So we verified that to the best of our numerical possibilities, indeed, our peaks that we observe in the fidelity susceptibility obey this scaling. So here what you see is that we are varying lambda in this clock model limit, and we have first the disordered phase, then there is this peak of the fidelity susceptibility in which the ground state is changing very fast. Then we have the gapless phase, second peak, and the ordered phase afterwards. So these entanglement properties are consistent with the appearance of a BKT phase transition. Yes.
It just might be a naive question. Maybe I didn't pay attention. The shaded part, which you said it's a gapless.
Yes.
Could I tell that from the order parameter? Like, could I tell that there's something happening here?
So here it's admittedly hard. In principle, you can do finite size scaling. You see that here I'm taking 21, 41, and 81. So the difference is that if I take the order parameter here, it decays exponentially with the system size, or at least this is what I expect in large system sizes. Here instead, it should decay as a power law. Well, I admit that we have too little point to see that. So, but
I understand that it goes in the ordered phase as a power, should go as a power law because you're in 1D, I guess. Is that the argument?
So we are in 1D, and this is a gapless phase. So essentially, this kind of order parameters that, as we were pointing out, are string order parameters decay algebraically. Okay. And this is something that I can justify soon with my field theory construction. And instead here, it converges to a finite value. So if you go to the thermodynamic limit, you would expect still something flat and then something that goes to a finite value here at discontinuity. Okay, good. So indeed, if we want to understand a little bit better what's going on, what we did was to build a bosonization description of this model. And in particular, here, I don't have the time to go in full detail, but what I'm doing is that I'm introducing 3 pairs of dual bosonic fields, and they are essentially related to the matter degrees of freedom in the 2 legs and to the gauge boson degree of freedom on the rank, such that theta is related to the phase of zeta or with the connection sigma, and instead these phi's are related to the electric field, essentially. So in this way, if I do this mapping from the discrete degrees, so the discrete operators to these vertex operators that I have here, I can go into the continuum from my lattice model, and I will get a Hamiltonian of this kind. So Here I have 3 different Lattinger liquids that are the first line. And these 3 different Lattinger liquids are describing essentially for S equal to 0, so for the rank degrees of freedom, it's the plaquette term and the electric field term on the ranks. And instead for S equal to up and down, so for the lag degrees of freedom, they are describing the tunneling and the mass term. On top of that, I have additional interactions that appear as this kind of Sine-Gordon interactions. And these Sine-Gordon interactions amount to the tunneling term along the rank and to the electric field terms along the legs. However, there is a problem. And namely, if I do that naively, I get a model that is U1 symmetric, and it's not Zn symmetric. Therefore, I wish to break down the symmetry of this model, and I do it by adding some additional Sine-Gordon terms that I call background terms that impose that the symmetry for the theta fields and also for the phi fields is indeed Zn. And you can see it because these isolate several minima of this theta and phi that depend on n. So I have n inequivalent minima. And these P and Q are parameters that you may think to be large that depend on the parameters of my model. This is a difficult question. So again, I think this is something that slightly depends on the boundary conditions. I would say that, let me think. Yeah, it depends on the boundary conditions. So I may have a residual global Zn symmetry if I have smooth boundary. And this in my model with the axial gauge would correspond to the product of all the etas. And there can be more. So we can discuss about that. For example, Sergei Moros, I think that last week presented his work in which he had several symmetry protected topological symmetries in one-dimensional chains. And also in that case, it was important to consider which terms were included in the Hamiltonian and what were the boundary operators. So here the physics is similar, and maybe we go back to that later. Yes, so here I have chosen a specific gauge choice, so I got rid of some of the redundant degrees of freedom, it's true. There are issues here. So, for example, if I want a global gauge symmetry, I was telling you that it's a symmetry in which I take all the thetas, so the theta up and the theta down, so the degrees of freedom of the matter, and I shift them by a 2 pi over n. So I'm just sending zeta into zeta times e to the I 2 pi over n. Instead, if I try to do the same trick with the phi, actually these amounts to change the background electric field. So it's a shift of the theta vacua, or I can see it as introducing additional charges at the edge. So Andrea's telling me that my time is running, so I don't want to go into the details, but essentially, bottom line is that I can compare what I get from the dmrg calculation to this bosonization by applying second order RG calculations. And the bosonization gives me a pretty good picture that is reliable for intermediate values of lambda and G, in which I find that there is a single gapless phase that is surrounded by a unique gap phase that is all adiabatically connected. And I'm drawing with different colors, different regimes that are connected through crossovers. In particular, the field theory predicts more phases than what they are observed in the dmrg. And this is due to the fact that this mapping between my Lattinger parameters and the parameters in the lattice model, it's not precise, it's not exact. So what I see here is a kind of zoom in, so zoom out of the truth. Probably adding additional terms, I would have obtained also other phases. But so the bottom line is that what I see are essentially 3 gapped phases that are the X phase, the confined phase, and then there is a third phase that I call quadrupolar. The quadrupolar phase is still a confined phase, and it has a weird property, namely there is a combination of the mesons that is ordered, and in this respect is not a confined phase, and another combination instead decays. So let me be more specific on that, and allow me to focus on what happens closer to the clock limit. So to study these phases, in particular the quadrupolar Coulomb and Higgs phase, I may introduce several gauge invariant observables, and the main ones are these mesons. And I can pick either a meson on the top leg or on the bottom leg, but I can also take products of these two mesons. And if I take the products of these two mesons, I may think about a string that moves two charges from the left on the right in the two legs, or a string that takes a dipole from the left and the right, and it moves it. So this string of the dipole is indeed what characterizes the quadrupolar phase. In terms of the field theory, what happens is that I can combine the 2 degrees of freedom of the fields up and down into a charge and spin sector, so sum and difference. And what happens is that the sigma sector, so the spin sector, is always gapped and always ordered across these phases. Instead, the charge sector is disordered, gapless, and ordered. And this can be also seen through second order normalization group. So at the level instead of what happens inside the gapped phase, as I was mentioning, there are several crossovers. These crossovers are characterized by maxima of the susceptibilities of the system, but these are not peaks that diverge. So everything is smooth, everything is continuous, and so they are adiabatically connected. And to characterize these phases, I can look at screening properties. As before, we can introduce static charges. And here we see what are the differences between the Coulomb, the quadrupolar, the Higgs, and the confined phase. So in the Coulomb, when I add static charges, I have an electric field that decays algebraically away from the static charges. And actually, let me show you the electric field directly. So these the first one is the behavior, the algebraic decay of the electric field away from the charge. In the quadrupolar phase, I have instead that the charges, the static charges determine the appearance of these strings of electric field that are not screened. And therefore, the electric field becomes essentially constant in the middle of the two static charges. In the Higgs and confined phase, instead, I have strong screening. And this implies that the electric field decays exponentially because there is dynamical charge that creates a screening cloud around my static charge. And we analyzed many different observables, the mesons, the Toft kind of strings, etc. But I don't have the time for that, so let me conclude. What I looked at are indeed ladder models in the lattice, so the lattice gauge series in ladder models, because I was interested in seeing what happens when we include plaquette operators in these models. And we performed our analysis by developing a useful bosonization technique that can be generalized to most of Zn models. And it's pretty powerful also for discussing clock models or frustrated clock models. And in parallel, we compared our results with dmrg. One of the main features of the Zn models is that in this one-dimensional setting with the ladder, there is a gapless phase, that is a Coulomb phase, that appear for n greater or equal than 5. If we try to extend this to a truly two-dimensional system, however, we run into trouble because this gapless phase disappear, and the physics is essentially dictated by the fact that these Zn deformations of the U1 theory are dangerous, irrelevant. And however, let me also point out that so we use dmrg, but one possibility to address dimensional system would be to extend tensor network calculations to PEPs, and it can be done by fulfilling the gauge symmetries. So here I finish. Thank you for your attention.
I'm a little puzzled by the n going the infinity limit of your work.
Okay.
Because in that limit, your variables all commute.
Well, in that limit, I get a kind of rotor model. Still, my observables have a kind of dynamics. So I would disagree on the fact that they commute. So I truly have.
So that's exactly my puzzle. If they commute, I could simply diagonalize the Hamiltonian.
No, but they don't commute.
They
So,
don't commute.
you know, the A field and the E field that you get in the limit, they do not commute with each other.
But your clock and the shift operators commute, right?
No, they have a tiny phase of difference.
So do you have some scaling of G and lambda with n that can?
I believe that, yes, one should consider that. Let me think, because so this U1 theory, if we want to go to QED, it's clearly appearing in the limit of the row. So I send the plaquettes to have smaller and smaller sizes, such that my cosine becomes b squared and the cosine of the electric field becomes e squared. So I believe that to do it properly, one has to do it. At the level of results of the RG, let me mention that if we increase n, my RG equations can be solved, and the Coulomb phase gets extended and bit squeezed, and all the gaps decrease.
About the Calabrese-Cardi formula you have, so
Yes.
do you have this addictive term, no? The additive term, sorry, that usually comes from the open boundary condition, C alpha. Do you have an estimation of this? Because usually some people say that, you know, part of this is universal and is, you know, the so-called boundary entropy by.
I must admit that I haven't checked. So I should check. In our numerics, for sure it's there. And I can probably also tell you what happens comparing periodic and open boundary conditions, but now I don't know.
Two questions.
Yes, I expect so. However, it's not so trivial. Namely, I thought about extending this to several legs, and we sketched something in our paper. The point is how you deal with the renormalization group. So as long as the renormalization group is done in a 1D fashion, then the quadrupolar phase essentially survives. If I do the renormalization group in such a way that I send both the L to infinity, but also the number of legs to infinity, then I should end up instead in these more complicated two-dimensional models. So in short, yes, the quadrupolar phase is an artifact of the ladder choice. There will be something similar that appears when you have a finite number of legs, and probably its effect, however, will be smoothed out. And it's also important to consider what are the boundary conditions. So if you put more legs, so you could decide also to have different boundary conditions on the legs and have also the ranks coming out. This may also affect the presence of this phase. And in particular, if you look at our model, we are breaking the usual duality between one limit and the other. And this is indeed an effect of the choice of the boundaries in the y direction. Yes. So to get the parafermions, you have to switch off the electric field along the legs, and you need to apply a Jordan-Miner transformation. So you have a unitary non-local transformation that maps essentially our rank degrees of freedom into a model of parafermions. Then, exactly, yes, I agree with that. And there is some subtlety, however. If you want to have truly parafermionic zero-energy modes, you must also break chiral symmetry. So you need to go into a chiral clock model. And in this description, this accounts essentially for adding a sort of background magnetic field. If I do not add this background magnetic field, so I take as the plaquette term just this sigma, sigma, sigma dagger, then I end up in the limit in which I have only weak topological order at the level of the parafermions. And this is due to the fact that you may end up having ground states that behave well at the level of topological order, but as soon as you consider excited states, you lose topological order. We can discuss about it more. So I have also works on non-abelian groups doing that job and generalization of parafermions to dions. Thank you for all the questions. Thanks.